share my screen first. So you can see my screen, right?
Yes.
Okay, fine. So today we will learn about GANs. This is Generative Adversarial Networks. So what are these GANs? These are a type of deep learning model that consists of basically two parts, a generator and a discriminator, that are trained in an opposite, or you may say competitive manner. Okay, and the work of goal of generator is to generate the fake images that look like real, and the goal of discriminator is to differentiate between those images as much as possible. So these two work in an opposite manner while training. So this is like chat gpt, so this is a part of like gen ai. So if you see that ChatGPT reached 100 million monthly users in just 2 months as compared with other apps, you can see. So the main role, the main like models or who are working on this area, these are people from universities, researchers, then companies, and there are many open source community like you may have seen Hugging Chat, Cave, or TensorFlow, PyTorch. These has open source communities which are working on this. So a simple example of this is how it will work. So we will have some training data. For example, here we have these images like boat, trees, water lily in the pond. So we will train the model. Okay, this model refers to both the generator and discriminator. So when we give, like we will ask, give some prompt. Okay, then this trained model will generate some new content. For example, uh, when we train this model, if we say, okay, give me a wide angle shot for from below of a female astronaut, then this model may give this kind of image. So this is completely new image. Okay, it was not present anywhere. Or you can also ask to write a conversation. For example, here you can write a conversation between the sun and Pluto. So now this is just an example. So there are still lot of like challenges and risk in this area, and there are a lot of opportunities as well. So let's come to the main architecture of GAN. As I said, that it consists of two neural networks, two main parts, generator and discriminator. So here you can see there is a generator, and here it is discriminator. So this generator is responsible for generating new data, while this discriminator distinguish between the real data and the generated data from generator. For example, we have this training set here. This is the real data. Okay, so a sample from this will be sent to discriminator, and this generator, we will give it some noise like random distribution. Okay, so generator will generate some data, and it will also send to the discriminator. So the job of discriminator here is to identify which one is fake, which one is real. Okay, and like earlier, obviously there will be like it is generator is generating data from the noise. So there will be more. What should I say, that like discriminator will be easily recognizing what is real and what is fake. Okay, so it will send the loss back to the generator, and this will help in fine tuning generator. Okay, so basically generator here tries to fool the discriminator by generating more realistic data. So this is a sample data set. So this was MNIST data set. Okay, So this is, we are selecting some real sample, like we mentioned here, that we select some sample. Okay, then see some random noise, okay, which we will be sending to the generator, which has like input layer. Okay, then hidden layers are there, output layer is there. So it has output layer of 28 by 28. Like this is the dimension of the image. Okay, so it will generate this fake sample. So this is the discriminator which will discriminate between the two of those. And because it will be only like yes or no, this real sample will have label 1 and this fake sample will have label 0. So it has to distinguish like 1 or 0. So for binary ones, like this is a now binary class problem. So in the output layer, we have only one neuron. Okay, so here it is the like first the discriminator will be like trained. So the same thing. Okay, the generator will send some fake data coming from this noise vector, generated from this noise vector to discriminator, and these real instances which will be labeled as y is equal to 1 will also be sent to discriminator, and the discriminator will be trained. It is more easy to train the discriminator as compared to the generator because it is like a simply binary problem. So you can train it easily to uh, differentiate between fake and real ones. And for training the generator, what you have to do, you will say, okay, on one more thing to remember, that while training one thing, we will keep the thing fixed. Like when you train the discriminator, we don't train the generator. We will keep the generator fixed. Okay, and while training generator, uh, this spelling mistake, sorry. Okay, so while training the generator, we will keep the discriminator fixed. So now you can imagine, okay, discriminator is fixed. Okay, so now you will train the generator. So the noise which is coming from this, you say, okay, this has the label 1. So you try to fool the discriminator. So still if discriminator is okay, it is giving it 1, like this generated image has one label. So it means that your generator correctly is correctly able to fool the discriminator. But if it correctly identifies it that it is a fake image or fake data, then you still need to like back propagate and uh, improve your generator by updating those weights and bias as we done in the first class. We discussed how weights and biases are updated in the neural network. So it will happen in the same way here. So this is the loss function, like how we update the weights and biases. We need loss function which will be coming from here, like how a discriminator is able to recognize the difference between fake and real. So the loss function for binary cross entropy we have done y log y hat plus 1 minus y log 1 minus y hat, where y hat is the predicted one, y is the original value. So for the data coming from, so this original distribution, this is called, uh, can I draw something? Sorry, 1 second. I think I didn't install that one. Okay, so maybe can
Maybe you can
configure.
just use MS Paint and drawing that.
Okay. So this one, this distribution is P X data, where X refer to the data point. Sorry, I'm not good at this. I'm doing it for the first time. Okay, so this is P data of X. This is the original distribution. Okay, and so for the label for the data coming from P data X, this is Y is equal to 1 because this is the original data, right? So, and corresponding to this, the predicted value will be, okay, predicted value for this one will be dx. Okay, so, and for this one, like y is equal to 1, so this term will be 0, and this predicted value will be dx, which refer to the hmm, which is the probability that x will be coming from the original data set. Okay, so this dx shows that our data will be coming from the original data set. So this shows that probability will be put back into the formula. We will get this expression. Okay, and for data coming from there, now this was from the original sample data. Now for the data coming from generator, okay, this one will have y is equal to 0 because this is the fake data. Okay, so y is equal to 0 and y has equal to g of x. So what is g of z? Sorry, g of z. So this is your z, some random distribution. Okay, so when you pass it through the generator, you will get the output which can be written as g of z. Okay, so the the probability coming from this one, this generator will be y has d g of z. So when we put this back into this equation, this will give y 0. So first term will be 0 and the second term will be log 1 minus d g of z. Okay. The what will be the objective of discriminator? It wants to maximize this and this term. Okay, these two terms, because you can see if it will be maximizing this one, what does it mean? That this shows the data come from the real training sample, like real data. Okay, so this should be like this should be close to 1, this should be maximum, and for this one we want that this should be like because it is coming from the generated fake data, so this should be 0. Okay, so it tries to maximize this whole term. It will be maximum when this will be 0, right? Then it will be log 1. And so the objective of discriminator here is to maximize this function. And what will be the objective of generator? Just the opposite. It will try to minimize this function. Now, in the part, this won't be taking any place, okay, because this is coming from the real training sample, and as from this image, the generator is not like directly making any contact with the real training sample. They both are sending the data to the discriminator, right? So the generator, we have only this loss term, and it will try to minimize this one. What does it mean? That it will try that dgz should be having maximum value. Okay, So what will be the value of the best discriminator and generator? For a fixed T, as I said, we train the discriminator, the generator will be fixed. So for a fixed generator value, or what we can say generator model, what will be the best optimal discriminator will be having p data of x, means probability that data is coming from the real sample, divide by probability the same one plus probability distribution from coming from the generator. Okay, so this is the optimal discriminator value for a uh, like a good best discriminator, and the role of generator is reverse of discriminator. So the optimal value will be when loss function is minimum, as I have said that it will try to minimize this loss function. So when loss function is minimum, while this discriminator will be equal to the best discriminator value, this dg star. Okay, so at this point these two will be equal. What does this mean? That probability distribution from coming from the original data is equal to the is same as the probability distribution from generator. Okay, then we can say that yes, exactly our generator is able to reproduce the exact probability distribution as similar to the original data. So PG is equal to, these two are equal. And at this point, if you do the whole calculation for the generator, okay, then it will give this value. And for digits are obviously this will be 2, this will be like 1 by 2 value something. Okay, so actually uh, we can give this mathematical formulation, but it is not possible to calculate this one. Okay, we can write mathematically, but when you work on your data, you won't be able to calculate this value because this distribution, the original input distribution is not known to us. We don't know how this one is there. Okay, so we can write mathematical expression, we can understand, but we won't be able to calculate for a real data set. And this is the ideal case, okay, that these two will be equal. And the ideal loss for this generator is, for the discriminator is zero point 0.5. Like this can give probability, that discriminator can give probability from 0 to 1, because in the output layer we will have this sigmoid function which we have discussed for binary class problem. Okay, so if your discriminator is having probability zero point 0.5, okay, zero point 0.5 is the probability for discriminator, then you can say okay, this is able to correctly, I mean our generator is able to foolish the discriminator, because now from the discriminator it can't tell whether it is real data or fake data. It's giving the probability zero point 0.5. It could be either real or fake. Okay, so our generator is like well trained here. This is a pictorial representation taken from this Goodfellow paper. Okay, so in this one, this dotted black line is the original distribution. This green line is coming from the generator. Okay, and these blue are random. These blue are coming from the discriminator. Okay, so this is original. This is coming from the generator, and this one is coming from discriminator. So these will need a lot of iterations, a lot of epochs will be required, because as I have said that a generator initially would give good results because it is trying to generate data from the noise. Okay, so for example in this one, You can see that generator initially it was randomly giving some values, but later like for the real samples, it is able to a little bit, not very good, but yes, it can say that okay, this is real. It is giving a higher probability to real data. And when at this point, when the data it says that okay, this is fake data, so the probability it will go near to zero for the discriminator, while our fake data has peak here. So our generator is correctly identifying here that it is a fake data. So in first step, we will train our discriminator. Okay, so here it is correctly identifying, okay, this is real data, and it is giving 0, and identifying, okay, it is a fake data. This is not real. This green line is not real. Now keeping this discriminator fake, okay, we train the generator. So you can see that generator, this green line is coming more closer to the original distribution, right? And as we go through more iterations, you can see that it almost matches the original distribution. And here the value of discriminator, it will output zero point 0.5. This is the value that now it no longer able to determine whether it is a real or fake data. So this is just an example that we try to fool the data with the picture of puppies and bagels. Okay, so it tries to learn from the data what is real, what is fake. Okay, and then this generative model, if we say okay puppy, then it may generate it, but sometimes your models also may hallucinate like this. There are a lot of these kind of, there are much similar images, okay, like images of cakes or muffins. In muffins you can why do something, raisins are there, okay, so it may be hallucinating those with the puppy's eyes. So a lot of training will be needed, and you need to check carefully. These have lot of business applications as well. Okay, and there is also from this model, like those vanishing gradient problems can exist, and the one major disadvantage is mode collapse. So what is this? That the generator, it produces a very limited variety of outputs instead of capturing the diversity of real data distribution. What does this mean? Suppose our data set has many images of various animals. Okay, but a generator, what it can do, that it will produce only images of cats, ignoring other animals like dogs, birds, elephants. Okay, so it only this one type of animal. Why this happens? Because you can imagine that we say that the generator try to fool the discriminator. Suppose it is generating images of cats, okay, and the discriminator is not able to identify those images whether it is real or fake, okay, as compared to other animals. So what it will say, that okay, this is good one, so it will try to the generator will try to focus only those images, because we are not asking it to exhaust yourself, we are not asking it to diversify, we are just saying that do your best for the discriminator. Okay, so it may generate only one kind of images, and say that okay, discriminator is not able to identify, so all is good. So this problem is called mode collapse. So to handle this problem, we can use more advanced architectures, like there are many various versions of GANs available now. So this is one version, Austrian GAN, which can help stabilize training. And also we can say that mini batch discrimination. In this one, this discriminator took a batch of samples together so that it can keep the it can help to detect and penalize the lack of diversity. So this is another variation. So these are just a very small number of different versions of GANs. There are many outside deep convolution GANs in which the convolutional layers CNNs are present in generator and discriminator. This is mainly for generating images. Okay. Then we have conditional GAN, Adversarial, which we have discussed just now. It okay. It uses some this distance as a measure of difference between real and generated distribution. You see, if it generates the only one like kind of samples only for cats, it the distribution will be different. The distribution won't be similar to the original distribution, right? So by using some different distance like they are using, it's possible to stabilize your training. And these are applications of GAN, least square. Okay, different. We have just read. It will be least square loss function. Then we have the super resolution GANs, which are very good to produce high resolution images. Big GAN. Okay. Then we have stack GANs. These are all GANs. To, so there is an interesting website. I don't know if you have heard that name. So that is person. If you go to this person, okay, GANs. It will generate a different image and you can see the resolution of these images. Okay, this is also like generating accessories.
Hi Vijaya, is Swati joining right now?
I think she lost her connection.
Sorry, you are not audible.
I think she lost her connection. I think so. Am I
Okay,
audible?
okay. Yes, you are audible.
Yeah, her voice all of a sudden start breaking. Yes,
Okay, let's wait her to join again.
I had texted her. She didn't.
Sure, okay.
Maybe the network come back. It will take time.
Sorry. Sorry, I was talking, like I was continuously talking, and then I just take the messages. So can anyone tell what was the last step I was at?
You
Mm,
close the slide.
sorry.
You close, just close the slide. That's it. You haven't
Uh,
showed the code.
sorry, I couldn't understand you.
Uh, you ended the slide. That's it.
Okay, I just sent it. Oh, oh, okay. Sorry. So did I have you seen this website?
Yeah, till there we saw it.
Okay, okay, then I need to show the code. Okay, okay, then I can start again. Maybe I will go fast. So here we are. First, we are trying to do with work with some MNIST data set. This MNIST data set has images of digits like 0, 1, 2, 3, 4, 5 up to 9. So we are loading this data set and doing some transformation, converting it to tensor, and then normalize the pixel value from between -1 to 1 using mean zero point 0.5 and standard deviation zero point 0.5. Okay, so if you see that the first image in this MNIST dataset has label 5, and you can see the tensor here. Okay, and this tensor will have value from between -1 to 1. As I have mentioned that we have normalized it between -1 to 1 with using this mean and standard deviation. So if you just want to see what was the image, so you can denormalize the function and then you can see this digit 5. Okay, this is from the data set. Then we are loading this data set. So here I am checking whether I can use GPU or not. Here first we will define discriminator. So the size of the images in this MNIST data set is 28 by 28. So if you multiply those two, 28 into 28, it will be 784. Hidden size 256. This is the number of neurons in the hidden layers. Okay, so we will define this network for the discriminator. We are using leaky ReLU activation function here. And in the output layer, we are using sigmoid. This generator will tell whether it is fake or real, 0 or 1. And for binary class classification, we use sigmoid function, right? In the next step, we will define the network for a generator. And here we are defining the input dimension 64, like coming from the random distribution noise, you can say. So first, here we see how this noise data, noise image will look like. So we are generating some random distribution using this generator network. This is just to see, okay, we are not doing any training or anything here. We are just seeing how these images will look like, which will be coming from the generator. These are all just noise. You can see there is nothing visible. This is only noise here. So to train it, first we will define the criteria, that is binary cross entropy loss function. We will give optimizer and the learning rate. Okay, then we define a function to train the discriminator. Here we give the real label value 1 and the fake label 0. Okay, then outputs will be when D will be this discriminator will be applied on real images. Okay, then the this outputs will come, and discriminator loss with the real images will be computed with using these outputs. Okay, and the real labels, because this is coming from the real data set. So these will be compared with these ones. This will be our D loss real. Now for fake images, these will be generated, okay, using random distribution, and fake images will be like this is this will generate some random distribution. Now when we apply generator on it, then we will have some fake images. So when discriminator will work on these fake images, it will generate some outputs. So when we compare these outputs with the fake labels, now see we have these fake labels here, but this is coming from the generator. So we will compare it with the zeros. Okay, so this D loss, like the discriminator loss, will be sum of real plus fake. This is the same loss function we have seen here, that this one coming from the real distribution and coming from the generator generator generated distribution. So then it will, like we are giving that it can adjust the weights and biases using back propagation. Similarly, we define a function for the generator. In this one, it will generate some images, okay, fake images. Then we give the labels, like we define these labels as ones, okay. Then generator loss will be if this discriminator, when it will be applied on fake images and it is compared with labels, how much it is like able to distinguish, like here labels are ones, okay. So we are trying to fool the discriminator here, giving it the fake images and comparing it with the label ones. So that will be our generator loss. And in a similar way with back propagation, this will be also trained. So here we are defining a directory, okay. This is the image from the MNIST dataset. And here we are defining function to save the images coming from the generator, okay. So generator will have some will generate some images, so we are saving those to see how well those images will be generated after each epoch. Here we are taking like 100 epochs, okay. So we are first defining those empty lists for discriminator loss, generator loss, real score and fake score. This is all like so when we are doing this training, these values will be keep updating, okay. It took me a long time to run, okay. So this was the image. I want to show you the first image as well. Like this was after 100 epoch, okay. The generator is generating this image, but for the first epoch or others, so this is the first epoch, you can see nothing is generated, okay. Then you can say after in fourth epoch what is there, so still nothing is there, okay. Then we can see at like this is 42, some numbers are visible now, you can see some numbers. So in this way you can check how your generator is improving in generating those fake images. So this is at epoch 100, and this one which I am showing here, this one is at the last epoch for 300. There is still some like blurred value, so maybe if you run for more epochs, this will be more cleared, okay. So we are saving this model. As I said yesterday, it is always good to save your model after running to use them in the future. So here we are giving the discriminator loss, this one blue one, and the generator loss. So as initially I have said that the generator is generating the images from noise, and you have also seen that images there was only blurry images, there was lot of noise. So at first the generator's loss will be very high and slowly it will start decreasing. And for generator as well, earlier it could easily recognize the images. Okay, so generator loss may increase a little bit. Okay, these are the scores, real and fake. So I have mentioned that a good model will be when the discriminator will have, when these scores will reach up to zero point 0.5. When these both real and fake score will come close to zero point 0.5, that will be good model. Okay, still it needs to come here. Okay, so maybe still more epochs will be needed here. So you can try with more epochs or giving more layers. Here we are just saying nothing else. So this is the whole framework. First we define our trainer and generator. Okay, then we run this model. So any doubt from here?
You mentioned 300 epoch. How long it took?
These 300 epochs, it took me 1 hour. It depends, like this was only grayscale images, right?
Yeah.
So this took less time. I also worked on another one. It is the same, like almost similar method using generator and discriminator only, but with 3D images. So here I had some anime images. Okay, so I have this red, green, blue channels. So I did the same thing here, working on training. So in this, only 25 epochs took me 1 hour because for high resolution images and also 3D images.
More, that means more quality images tend to take more time.
Yes, but still images take less time than the text data, I believe. Because yesterday when I was showing, even 5 epochs are taking 1 hour. So I think it is from my like work experience that images still take less time than the text data.
Okay.
So I think from my side it is over. If there are any questions, if not, maybe Trishika can start if she is here.
We will have session tomorrow.
Okay.
Okay, so you are done, right?
Yes, I'm done. Okay, so I will stop sharing.